Gravity feels obvious. You drop something, it falls. You jump, you come back down. You stand on the ground and feel your weight pulling you toward Earth. It feels so natural that most people never question it. Gravity becomes one of those ideas we think we understand just because we live inside it every second of our lives. But this feeling of familiarity is exactly what hides the truth. Because what gravity really is and how it truly works is nothing like what it feels like. In fact, almost everything you think about gravity is backwards. From the moment you are born, gravity shapes your body without you realizing it. Your spine grows under its pressure. Your muscles strengthen to fight it. Your heart learns how to pump blood upward against it. Even the way you walk, the way you stand, the way you sit, the way you breathe is quietly controlled by gravity. It becomes so normal that your brain stops noticing it. Just like you stop noticing the air you breathe, you stop noticing the invisible force that is holding you to the planet. And that is where the misunderstanding begins. We say gravity pulls things down. But what is down? Toward your feet, toward the floor, toward the center of the earth. If someone stands on the opposite side of the planet, their down points in the exact opposite direction to yours. Yet both of you feel perfectly upright. Both of you feel like you are standing on solid ground. Neither of you feels like you're upside down. That alone should already feel strange. If down changes direction across the planet, then down cannot be a universal direction. It is not a true direction of the universe. It is a local illusion created by gravity. Now imagine zooming out into space. There is no up, there is no down, there is no left or right in the way we understand it on Earth. Those directions only exist because gravity pushes us against the ground and gives our bodies a frame of reference. Without gravity, your sense of direction slowly dissolves. Astronauts often report that after spending enough time in space, they lose the feeling of which way is up entirely. They flip effortlessly. They rotate without realizing it. Their body no longer has a preferred direction. So if down is an illusion, what is gravity really doing? Here's the sentence that almost nobody hears growing up. You are not being pulled down by gravity right now. You are being pushed up by the ground. This sounds wrong the first time you hear it. You feel heavy. You feel like something is pressing you into the floor. You assume that is gravity pulling you down. But in truth, gravity is trying to make you move freely. Gravity is trying to let you fall. The only reason you are not moving is because the floor is blocking that fall and pushing back against your body. If the ground were to suddenly vanish beneath your feet, you would not feel heavier. You would not feel a sudden strong pull. You would feel weightless. For a brief moment, you would feel exactly like an astronaut in orbit. That strange floating feeling you see in space is not caused by the absence of gravity. It is caused by the absence of the ground pushing back. Gravity would still be acting on you in that moment, but you would not feel it anymore. This flips everything upside down. You don't feel gravity when you're falling. You feel gravity when something stops you from falling. Astronauts orbiting Earth are still under the influence of Earth's gravity. If gravity disappeared, the moon would drift away and astronauts would fly off into deep space. But gravity is still pulling on them. The only difference is that there is no ground to push back. They're falling continuously around Earth, missing the surface again and again as the planet curves away beneath them. That endless fall is what we call orbit. That endless fall is what feels like floating. So when you stand on the ground, what you feel as weight is not gravity itself. It is the resistance of the ground pushing against your body. Your bones compress, your muscles tense, your skin slightly deforms. All of that creates the sensation you call weight. Remove the ground and the sensation disappears, even though gravity remains. This means falling is not the strange state. Standing still is the strange state. In the natural behaviour of the universe, everything that is free falls. Planets fall, moons fall, stars fall, galaxies fall. They fall around each other in endless curves guided by gravity. The only reason you don't fall freely right now is because your planet is physically blocking your motion. You are constantly being held back from your natural state of free fall. This is deeply unsettling when you really let it sink in. It means you're not resting peacefully on the Earth. You're being violently pushed upward by trillions of atoms in the ground beneath you. The surface of the planet is not gently holding you. It is resisting your fall with enormous forces at the atomic level. Every time you stand still, you are locked in a microscopic battle between gravity trying to let you move and matter preventing you from doing so. Now imagine for a moment that the Earth was suddenly to vanish beneath you, replaced by empty space. There would be no explosion, no dramatic pulling sensation. You would simply begin drifting. You would float, just like astronauts do. You would feel weightless, even though Earth's gravity would still be acting on you for a short while. The sensation of falling does not feel like being pulled. It feels like freedom. This is the great illusion of gravity. It feels like a force dragging you downward, but in reality, gravity is the geometry of motion itself. It is the natural path that everything follows when nothing is in the way. From this single misunderstanding, countless others begin to grow. We imagine gravity as some invisible rope pulling objects together. We imagine the Earth reaching up to grab falling objects. We imagine planets being yanked along by some hidden hand. But gravity is not a hook. It is not a rope. It is not a wind. It is not a magnet. It is something far stranger and far more beautiful than that. Even the word force misleads us. We talk about gravitational force, but gravity does not behave like other forces. If you turn off electricity, electric forces vanish. If you remove a magnet, magnetic forces vanish. But gravity cannot be shielded. It cannot be blocked. It cannot be turned off. It does not weaken because of material in between. A mountain does not stop gravity. A wall does not stop gravity. A planet does not absorb gravity. Everything feels it, always. And yet, gravity is also the weakest force in the universe. This sounds impossible to believe. Gravity can hold oceans to the planet. Gravity can shape planets. Gravity can bind entire galaxies together. Gravity can crush stars into black holes. And yet, a small magnet in your hand can easily lift a metal object against the full gravitational pull of Earth. A child can jump upward against gravity with the effort of a few muscles. A bird can fly in defiance of gravity. A rocket can leave the planet entirely. So how can gravity be so weak and yet rule everything? That question will take us deep into the heart of this series. But before we go there, something even more unsettling must be understood. Gravity does not pull equally everywhere. You feel slightly more gravity at sea level than you do on a mountaintop. You feel slightly more gravity at the poles than you do at the equator. You feel slightly more gravity standing on dense rock than you would over empty caves beneath your feet. These changes are tiny, far too small for your body to detect. But they are real. Sensitive instruments can measure them. Space missions depend on them. Entire navigation systems depend on them. Gravity is not uniform. It is shaped by mass. It is guided by matter. It bends, stretches, intensifies, and weakens across space. This tells us something very important. Gravity is not acting inside space. Gravity is shaping space. This idea sounds poetic, but it is literal. Gravity does not live inside the universe like a force sprinkled on top of reality. Gravity is written into the structure of space and time themselves. It is the architecture of motion. It is the reason objects move the way they do when nothing interferes. When ancient humans looked at falling objects, they saw mystery. They saw a magical movement toward the ground. They had no explanation for why fire rose upward while stones fell downward. Some thought the earth pulled things home. Some believed objects had a natural desire to return to their proper place. The idea of natural motion was born, that heavy things wanted to move downward and light things wanted to move upward. For thousands of years, this idea survived. It wasn't precise, it wasn't mathematical, but it felt right. Stones fall, flames rise, that was enough. Then one day, a man named Isaac Newton watched an apple fall, and the story of gravity took its first true scientific step. But even Newton, with all his equations and brilliance, only uncovered part of the truth. His gravity worked beautifully. It predicted the motion of planets. It explained falling objects. It described the orbits of moons and the paths of comets. For over 2 centuries, it ruled physics. And yet, Newton himself believed something strange. He believed gravity acted instantly, across empty space. No delay, no medium, no mechanism. One object simply knew where another object was and responded instantly. Even across millions of kilometers, gravity was immediate. That idea bothered him deeply. He wrote that he did not believe gravity was a fundamental property of matter. He suspected there was some deeper truth underneath it. And he was right. 200 years later, another man would arrive and completely destroy our idea of what gravity is. But before that revolution, before space and time shattered and reformed, we must first fully understand how deeply gravity controls your everyday life in ways you never notice. Gravity decides how rivers flow. Gravity decides how mountains rise and erode. Gravity decides how air presses on your body. Gravity decides how blood circulates through your veins. Gravity decides how rain falls, how waves form, how clouds drift, how sand dunes shape themselves. Every moment of your life is being sculpted by gravity so gently that you mistake it for normality. Even the shape of your planet is gravity's work. Earth is not a perfect sphere because it spins. It bulges at the equator. That bulge exists because gravity and rotation compete with each other. Spin pushes matter outward. Gravity pulls matter inward. The shape of the planet is the compromise between those opposing influences. Even the moon exists, as it does because of gravity. Earth's gravity locks the moon into showing us the same face forever. One side always looks toward us. The other side is hidden. That tidal locking is the slow result of gravitational stretching across billions of years. The tides of the oceans rise and fall because the moon and the sun pull on Earth's water. Gravity literally drags entire oceans across the surface of the planet twice every day. You do not notice it because it happens slowly, gently, rhythmically. But trillions of tons of water move because of gravity's invisible reach. Even time itself is shaped by gravity, though that truth is so strange that it sounds like science fiction at first. Clocks tick at different speeds, depending on how strong gravity is around them. Time flows slightly faster on mountaintops than at sea level. Satellites in orbit must correct for this difference, or their navigation systems would fail. Without adjusting for gravity's effect on time, GPS would drift by kilometers every day. This means gravity is not just controlling motion, it is controlling time. And this is where the misunderstanding becomes complete. Gravity is not simply about falling. It is not simply about weight. It is not simply about attraction. Gravity is about the shape of reality, but our intuition refuses to accept this easily. We want gravity to behave like a familiar force, like a push or a pull. We want arrows and vectors and simple diagrams. But gravity does not operate inside that simplicity. It reshapes the very stage on which all motion plays out. That is why astronauts feel weightless even while still deep inside Earth's gravitational field. That is why planets fall endlessly around the sun without crashing straight into it. That is why light bends around massive objects. That is why time slows near black holes. That is why galaxies twist into spirals. That is why the universe itself expands and stretches. All of this traces back to the same misunderstood force: gravity. In this first part, you are meant to lose your certainty, to feel that the simple picture of gravity you grew up with is incomplete, backward, and misleading. Because only when the old idea breaks can the real one emerge. The ground is not your anchor. Falling is not the exception. Free motion is not chaos. And gravity is not a simple pull downward. It is the quiet architect of everything. And now that the illusion has cracked, the next step is to see how humanity tried to describe this invisible architect for the very first time, with an apple, the moon, and one man's attempt to turn mystery into mathematics. For most of human history, gravity was not a law. It was a feeling. Things fell. Heavy objects sank. Fire rose. That was enough for the ancient mind. People did not ask for equations. They asked for meaning, and the answers they created were tied to philosophy, not physics. The earth was thought to be the natural home of heavy things. The sky was thought to be the natural home of light things. Stones fell because they wanted to return to the earth. Smoke rose because it belonged to the heavens. This idea survived for thousands of years because it matched what people saw. Drop a stone, it falls. Light a flame, it rises. No one needed more than that. The universe looked simple, and so the explanation stayed simple too. But hidden inside this simplicity was a deeper pattern that no one could see clearly yet. The apple fell, the moon moved, the planets wandered across the sky, and no one knew that all of these motions were part of the same story. Then in the 1600s, everything changed. Isaac Newton did not invent gravity. Gravity was already there, shaping the world long before him. What Newton did was far more dangerous. He gave gravity a map. He turned mystery into mathematics. He linked falling apples to orbiting moons and told the universe that it had to obey a single rule. Before Newton, planets were a puzzle. They did not move in straight lines. They did not sit still. They wandered, ancient. Astronomers called them wanderers. Their paths were strange loops in the sky. At times they moved forward, at times backward. Entire civilizations built complex models of crystal spheres and divine mechanisms just to explain why these points of light refused to behave simply. Then came a quiet revolution. Johannes Kepler discovered that planets move in ellipses, not perfect circles. This was already a blow to centuries of belief. The universe was not built from perfect shapes. It followed stretched off-center paths, but Kepler only described how planets move. He did not explain why. Newton was the one who asked the forbidden question. Why? Why does the moon go around the Earth? Why do planets go around the sun? Why does an apple fall straight down instead of sideways or upward? The legend says the answer came to him when he watched an apple fall from a tree. The truth is less dramatic and more powerful. The apple did not give him the answer. The apple gave him the right question. If the apple falls because Earth pulls it, then why does the moon not fall too? At first this sounds like a mistake. Of course the moon falls. It falls all the time. But it never reaches the ground. It keeps missing the Earth, This was the insight. The moon is falling. It is just falling sideways. Newton realized that the same force pulling the apple downward is pulling the moon inward. The only difference is that the moon is moving fast enough sideways to keep missing the Earth as it falls. The moon is not floating. It is forever falling around the planet. With that single realization, Earth and sky became one system. The force that rules your body also rules the cosmos. Newton then did something revolutionary. He wrote gravity into an equation. Every mass attracts every other mass. Bigger mass means stronger attraction. More distance means weaker attraction. This was the law of universal gravitation. Suddenly gravity was no longer an Earth-only phenomenon. It became truly universal. The same rule that governs apples governs stars. The same rule that shapes your weight shapes the orbits of galaxies. For the first time in history, humanity had a single mathematical law that connected the ground beneath its feet to the sky above its head. And this law worked. It worked so well that it predicted the motion of planets with astonishing accuracy. It explained comets that returned after decades. It explained the tides of the ocean. It explained why Earth bulges at the equator. It explained why the moon stays locked to one face. It explained why planets form disks around stars. Newton's gravity turned the universe from a mystery into a machine. For over 200 years, no one seriously challenged it. With Newton's equations, engineers could design bridges. Astronomers could predict eclipses centuries in advance. Navigators could cross oceans using the stars. Artillery officers could calculate projectile paths. Everything that moved under gravity now followed precise, predictable rules. The universe had become clockwork, but buried inside this beautiful system was something deeply troubling. Newton's equation worked perfectly, yet it explained nothing about how gravity actually travels. It simply said that gravity acts instantly, across any distance. If the sun vanished at this moment, Earth would immediately fly off its orbit with no delay at all. Newton himself did not believe this was physically real. He famously said that the idea of gravity acting across empty space without any mechanism was so great an absurdity that no one with proper thinking should accept it. But his equation worked so well that people ignored the philosophical problem. Gravity became a ghost force, invisible, everywhere, instant. No one knew what gravity really was. They only knew how to calculate it. For centuries, that was enough. But even before Einstein arrived, cracks began to show. One of the first signs of trouble appeared in the orbit of Mercury. Mercury is the closest planet to the Sun. It experiences stronger gravity than any other planet, and its orbit did not behave exactly as Newton's laws predicted. The difference was tiny, almost invisible, but it was real. Mercury's path slowly shifted in ways Newton could not account for. For decades, astronomers searched for hidden planets or unseen influences to explain this strange motion. None were found. The error remained. Newton's gravity was shockingly accurate, but it was not perfect, and perfection mattered now. Meanwhile, something else was changing in physics. Light was being studied more deeply. Electricity and magnetism were being unified. Space and time were being questioned. The neat mechanical universe that Newton described was beginning to feel incomplete. Then in the early 1900s, a quiet patent clerk named Albert Einstein rewrote the meaning of the universe. But before we go there, it is important to understand something clearly. Newton was not wrong. His gravity still launches rockets. His gravity still guides space probes. His gravity still predicts the paths of planets. His gravity still engineers the modern world. Even today, when spacecraft travel to other planets, Newton's equations are often all we need. They are simple. They are powerful. They are astonishingly precise. So what went wrong? Nothing went wrong, but something deeper was still hidden. Newton treated gravity as a force that pulls through space. Einstein would reveal that gravity is not a force at all. And this is where everything you think you know about gravity begins to break. Because if gravity is not a force, then what is it? Before Einstein answered that question, one more puzzling fact needed to be noticed. All objects fall at the same rate. A feather and a hammer fall together in a vacuum. A stone and a wooden block fall together. A grain of sand and a mountain experience gravity in the same way. Heavy or light, the acceleration is the same. This is deeply strange. In every other force in physics, mass matters. A heavy object resists acceleration more than a light one. Push both with the same force, and the lighter one accelerates faster. That is how the universe normally behaves, but gravity breaks this rule. Under gravity, all objects fall the same way. This coincidence bothered people for centuries. Newton noticed it. Galileo tested it. But no one could explain why it had to be true. It just was. This single mystery would become the seed of Einstein's revolution. But for now, in the age of Newton, gravity had become law. It had become order. It had become the mathematical backbone of the universe. The sky no longer belonged to divine motion. It belonged to equations. The heavens were no longer a separate realm. They were ruled by the same physics as falling apples. This was one of the greatest shifts in human history. The universe became understandable, not emotionally, not spiritually, but mathematically. And yet, hidden behind the success of Newton's gravity was a dangerous illusion. People began to believe they fully understood gravity. They did not. They only understood its shadow. They knew how to calculate it. They did not know what it truly was. And that misunderstanding would last until Einstein shattered the idea of force itself and replaced gravity with something far stranger than anyone had imagined. But before gravity could be reborn as curved space-time, we must first confront an even more shocking truth. Gravity is actually the weakest force in the universe. So weak, in fact, that two people standing next to each other do not feel it at all. Yet somehow it rules galaxies. That impossible contradiction is where the story turns next. If you are asked to name the strongest force in the universe, most people would say gravity without hesitation. After all, gravity holds oceans to the Earth. Gravity keeps the moon in orbit. Gravity binds planets to stars, and stars to galaxies. Gravity shapes the largest structures that exist. It decides where everything goes. From that perspective, gravity feels all-powerful. But here is the truth that sounds almost impossible when you hear it for the first time. Gravity is actually the weakest force in the entire universe. Not just a little weak, not weak in some special cases. Gravity is unbelievably, absurdly weak compared to the other forces of nature. This single fact is one of the greatest mysteries of modern physics. It forces us to question everything we think we understand about reality. To see how weak gravity really is, you do not need a laboratory, a telescope, or a supercomputer. You only need a small magnet and a metal object. Hold a paperclip in your hand. Let it hang freely. The entire mass of the Earth is pulling that paperclip downward with its full gravitational strength. The Earth is not holding back. It is using all of its mass, all of its gravity, all of its invisible power to pull that tiny piece of metal toward the ground. Now bring a small magnet close to the paperclip. The magnet easily lifts the paperclip upward, overcoming the pull of the entire planet beneath it. That should shake you. A tiny magnet sitting in your hand just defeated the gravity of a world that weighs 6 trillion kilograms. This is not a trick. This is not an illusion. This is a basic comparison of forces. The electromagnetic force inside that small magnet is stronger than Earth's gravity acting on the paperclip. If gravity were even slightly stronger, magnets would struggle to lift anything. If gravity were slightly weaker, planets might never form. Stars would never compress. The universe would look completely different. Gravity sits at a strange balance point, weak enough to be defeated easily at small scales, strong enough to dominate at cosmic scales. And this is where its true nature begins to reveal itself. Gravity does not win by strength. Gravity wins by patience and reach. The electromagnetic force is far stronger than gravity, but it cancels itself out. Positive and negative charges balance each other. At large distances, most objects are electrically neutral. Their charges cancel. The strong nuclear force is incredibly powerful, strong enough to bind protons together inside atomic nuclei, but it only works over tiny distances. Step just outside the size of an atom, and it vanishes. Gravity is different. There is no negative mass. There is no way to cancel gravity. Every piece of matter adds to it. Every atom contributes. Every molecule strengthens it. Gravity never switches off. It never neutralizes itself. It only accumulates. This is why gravity rules over galaxies and clusters of galaxies. Not because it is strong, but because it never stops adding up. But this still does not explain something very strange. If gravity is so weak, why do you even feel it at all? The answer is hidden in the sheer number of atoms beneath your feet. Every second, trillions and trillions of tiny gravitational pulls from individual atoms inside the Earth combine to create the force you feel as your weight. Not one atom pulls you strongly, but together their combined influence becomes overwhelming. This is gravity's secret strategy. It never overwhelms you with power. It overwhelms you with quantity. And yet, even knowing this, one of the deepest puzzles remains. Why does gravity treat all masses the same? If you push a shopping cart and a truck with the same force, the cart accelerates faster. This is how the universe normally behaves. Force divided by mass gives acceleration. Heavier things resist motion more. But gravity completely ignores this rule. Drop a hammer and a feather in a vacuum, and they fall together. A mountain and a grain of sand accelerate at exactly the same rate under gravity. Massive or tiny, gravity does not care. Everything falls the same way. This strange fact is so unusual that it should not exist at all. Yet it does. And this is where gravity quietly whispers that it is not a normal force, because in every other force, the amount of force depends on the charge involved. Electric forces depend on electric charge. Magnetic forces depend on motion of charge. Strong and weak nuclear forces depend on special particle properties. But gravity depends on mass. And mass does two completely different jobs in physics. Mass tells how strongly something resists acceleration. Mass tells how strongly something creates gravity. These two roles appear totally unrelated, and yet, in every experiment ever done, they are exactly equal. The mass that resists motion is exactly the same as the mass that produces gravity. This is not logically required. The universe did not have to work this way. These two types of mass could have been very different numbers, but for a mysterious reason, they are perfectly identical. This coincidence is so precise that if it were off by 1 part in a trillion, the universe would behave differently enough that we would have noticed long ago. This equality is called the equivalence of inertial mass and gravitational mass. For centuries, it looked like one of those strange coincidences of nature that no one could explain, until Einstein noticed it and realized it was not a coincidence at all, But before we reach Einstein's revelation, there is another deeply uncomfortable truth we must face. Gravity acts instantly in Newton's universe. If the sun vanished right now in Newton's model, Earth would immediately feel the change. Not 8 minutes later, instantly, across empty space. This violates everything we know about how information travels. Even light has a speed limit. Even radio signals take time. Even cause and effect are limited by this speed. Yet Newton's gravity had no speed limit, no delay, no messenger, nothing moved. Gravity simply acted. Newton knew this made no physical sense. He openly admitted that he did not believe gravity could really work this way. But without a better explanation, the universe simply accepted this strange instant action as a mathematical convenience. For 200 years, physics lived with this ghost. Everything could be explained by Newton's gravity, except what gravity actually was. Then something even stranger appeared. Gravity does not behave like other forces near very strong masses. Near massive objects like neutron stars or black holes, gravity behaves in ways that Newton's laws cannot predict. Time slows, light bends, orbits warp. Space itself appears to stretch. None of this exists in Newton's universe. In Newton's model, space is flat. Time is absolute. Forces are arrows that push and pull within that fixed stage. But gravity refused to stay inside that simple picture. It distorted the stage itself. This is the point where physics quietly began to realize that gravity might not be a force at all, that it might be something deeper, something woven into the fabric of space and time. But before that truth could be revealed, one final question had to be answered. If gravity is so weak at small scales, why does it dominate the large-scale universe completely? The answer lies in how gravity behaves with distance. Gravity spreads out. It weakens as you move away, following a precise mathematical pattern. Double the distance, and gravity becomes 4 times weaker. Triple the distance, and it becomes 9 times weaker. This is called the inverse square law. Every force that spreads out in 3 dimensions behaves this way. But here is the key difference. Electric forces weaken with distance too, but positive and negative charges cancel each other out. At large scales, the universe is electrically neutral, so electric forces disappear at cosmic distances. Gravity has no negative partner. Nothing cancels it. So even though gravity weakens with distance, it never fully disappears. Across the vast emptiness of space, gravity is the only force that still reaches. Over millions of light years, gravity still whispers. Over billions of light years, gravity still pulls. Over the entire observable universe, gravity still shapes the web of galaxies. This is why gravity dominates the universe, not by strength, but by inevitability. Everything has mass, everything contributes. Nothing cancels it, nothing escapes it. And yet, this inevitability hides behind an almost laughable weakness at small scales. A child can jump against gravity. A bird can fly against gravity. A magnet can defeat gravity. A rocket can escape gravity. And yet, no star escapes gravity. No galaxy escapes gravity. No cluster escapes gravity. Gravity is weak where you feel it most, and unstoppable where you can never touch it. This strange dual nature tells us that gravity does not belong to the world of everyday forces. It belongs to the world of geometry. It belongs to the structure of reality itself. When you lift a cup, you fight gravity. When you throw a ball, you fight gravity. When you climb stairs, you fight gravity. But when a planet moves around a star, nothing is being pulled in the simple sense. The planet follows the only natural path available to it through curved space. This is where Newton's map ends and Einstein's reality begins. Newton showed us how gravity behaves. Einstein would show us what gravity truly is, and the truth will turn space and time inside out. But before that revolution fully arrives, one more everyday illusion must be shattered. If gravity is pulling you downward, why do you feel weight only when you stand still, and feel weightless when you fall? That question will expose the deepest trick gravity has ever played on your senses. And that is where the story turns next. At the start of the 20th century, physics believed it had almost finished its job. Newton had mapped motion. Maxwell had unified electricity and magnetism. The universe looked like a giant machine running on clean, precise equations. Time flowed the same for everyone. Space was a solid stage where everything moved. Forces pushed and pulled on objects like invisible hands. It felt complete, and yet hidden inside this perfect structure was a crack that no one could seal. Gravity. It worked, but it did not make sense. Newton's gravity could calculate everything, but explain nothing. It could tell you how the moon moves, but not why gravity exists. It could describe how planets orbit, but not what carries the force across empty space. It could predict the future with stunning accuracy, but it had no physical soul. Then came a man who did not try to fix gravity. He replaced it. Albert Einstein did not look at gravity and ask, "How does this force pull?" He asked something far more dangerous. What if gravity is not a force at all? This single question would pull the universe apart and rebuild it from the inside. Einstein began with a simple observation that everyone else had ignored because it felt too obvious to matter. If you are inside a sealed elevator with no windows and that elevator begins to fall freely, you will feel weightless. You can float, you can spin, you can let go of objects and watch them hover beside you. Inside that falling elevator, gravity seems to vanish. Now imagine the opposite. The elevator is in deep space, far from any planets. There is no gravity at all. But suddenly, the elevator begins to accelerate upward. You're pushed into the floor. Your feet press against it. Your body feels heavy. You feel weight again. In one case, you're falling in gravity and feel weightless. In the other, you're in empty space and feel weight. From inside the elevator, there is no experiment you can perform that tells you which situation you are in. To the universe, falling and floating are the same experience. This was the equivalence principle. It whispered something shocking. If falling feels exactly like floating, then maybe gravity is not a force you feel, but the absence of resistance. This insight cracked open the true nature of gravity. Einstein realized that mass does not pull objects through space like a rope. Instead, mass changes the shape of space itself, and objects simply move along the paths that space allows. This is where the famous rubber sheet analogy appears. Imagine space as a stretched fabric, flat, smooth, and even. If you place a heavy ball on that fabric, it creates a dip. A curve appears. Now, roll a smaller ball nearby. The smaller ball does not get pulled by an invisible force. It simply follows the curve created by the heavy object. It moves because the surface beneath it is no longer flat. This is not a metaphor for gravity. This is what gravity is. Mass bends space. Time bends with it. And everything moves according to that curvature. In Einstein's universe, the Earth does not pull the moon. The Earth curves the space around it. The moon simply follows the straightest possible path through that curved space. That straight path through curved geometry looks like an orbit. Nothing is being pulled. Nothing is reaching across space with invisible hands. Everything is just following the shape of reality. This is why gravity treats all objects the same, heavy or light, a feather or a hammer. They fall the same way because they are not being pulled. They are all following the same geometry. The geometry does not care about their mass, only the path matters. In Newton's universe, gravity is a force acting inside space. In Einstein's universe, gravity is the shape of space itself. This difference is so deep that it changes everything. It changes how light moves. It changes how time flows. It changes how energy behaves. It changes what straight even means. Even light, which has no mass at all, must follow curved space. That means light bends near massive objects. It does not slow down. It does not curve because it is pulled. It curves because space itself is curved. This idea was so radical that almost no one believed it at first. Then the universe tested Einstein. In 1919, during a total solar eclipse, astronomers measured the positions of stars near the edge of the sun. According to Newton, their light should pass straight by. According to Einstein, the sun's gravity should bend that light slightly. When the results came in, the stars had shifted exactly as Einstein predicted. Light had bent, space had curved, gravity had revealed its true nature. In one moment, Newton's invisible force was replaced by curved space-time, and the universe was never the same again. From that day forward, gravity was no longer the weakest force in physics. It became the architecture of the cosmos. It became the reason the universe has shape. Time itself stopped being universal. In Newton's world, everyone shared the same clock. Now, Einstein revealed that gravity controls how fast time flows. The stronger the gravity, the slower time moves. Clocks near massive objects tick more slowly than clocks far away. This is not a philosophical idea. It is not abstract. It is measured. A clock on your head ticks faster than a clock on your feet. A clock on a mountain ticks faster than a clock at sea level. A clock on a satellite ticks faster than a clock on Earth. GPS would fail without correcting for this effect. Without Einstein's gravity, your phone would be lost by kilometers every single day. This means gravity is not just shaping motion. Gravity is shaping time itself. Near huge masses, time slows dramatically. Near black holes, time almost stops. From the outside, objects falling into a black hole appear to freeze forever at the edge. From the inside, they fall normally. Two observers seeing the same event experience completely different realities. This is the true power of gravity. It is not how hard it pulls. It is how deeply it reshapes reality. Einstein's equations showed that space and time are not separate things. They form one connected fabric, called space-time. Mass and energy tell space-time how to curve. Curved space-time tells matter and light how to move. This quiet relationship governs everything. Planets orbit because space-time is curved. Galaxies spin because space-time is curved. Light bends because space-time is curved. Time slows because space-time is curved. And you fall because space-time is curved. You are not being pulled down. You are moving along a path shaped by Earth's mass. And the ground pushes you upward, resisting that path. This is why standing still feels heavy. This is why falling feels free. This is why astronauts float. This is why orbit is endless falling. Once you see gravity this way, everything becomes suddenly unified. The apple falls, the moon orbits, the Earth curves space, the sun bends time, the galaxy twists light. All of it is the same phenomenon at different scales. This is also why gravity becomes so dangerous near extreme objects. A neutron star is so dense that a teaspoon of its material weighs billions of tons. Space curves violently near it. Time slows dramatically. Light bends into arcs around it. Tides become so powerful that they can tear atoms apart. A black hole takes this to the limit. So much mass is packed into such a small region that space-time collapses into a point. The curvature becomes infinite. No path leads outward. Every possible future points inward. Not because gravity is pulling harder than ever, but because space-time itself has folded shut. In Newton's world, you could imagine escaping any force with enough speed. In Einstein's world, escape itself can be removed from reality. Once something crosses the event horizon of a black hole, all possible paths lead to the center. Not because something pulls it, but because space-time no longer allows any other route. This is not force. This is geometry turned fatal. Einstein's gravity also predicted things no one had ever seen. Gravitational waves, ripples in space-time itself. Not waves in space, waves of space. When massive objects move suddenly, like black holes colliding, the curvature they create does not adjust instantly. It ripples outward at the speed of light. These ripples stretch and squeeze space as they pass. They are gravity in motion. For decades, this was only theory. Then, a century after Einstein predicted them, humanity finally heard space-time ring. Two black holes collided over 1 billion light-years away. Their crash shook the universe, and on Earth, detectors the size of kilometers felt space-time stretch by less than the width of a proton. We detected the echo of a cosmic collision. Gravity had spoken. Einstein had been right again. Newton's gravity still guides our rockets. Einstein's gravity guides the universe itself. And yet, even Einstein's gravity is not the final story. When we try to combine it with the quantum world, the world of tiny particles, the equations break. Gravity refuses to behave like the other forces. It does not fit neatly into the quantum framework. It resists unification. It remains separate. Even after everything Einstein revealed, gravity still hides a deeper layer. We know how it curves space-time. We know how it bends light. We know how it slows time. We know how it builds galaxies. We know how it creates black holes. But we still do not know why it exists at all. We have mapped its behavior with astonishing precision. We have not uncovered its true origin. Gravity remains the most familiar mystery in physics. You feel it every second, but its true source is still unknown. And now that you have seen gravity not as a pull, but as curved reality itself, the next illusion must fall away completely. Because if gravity is shaping space-time, why do astronauts float? Why does weight disappear in orbit? Why do you feel heavy only when you stop falling? The answer will finally destroy the last everyday misunderstanding of gravity. And that is where the story goes next. Watch an astronaut inside the International Space Station, and something inside you immediately rebels. They drift gently through cabins. They push off with one finger and glide like ghosts. Drops of water form perfect floating spheres. Tools hover in mid-air. Hair refuses to fall. Everything looks unreal. And the first thought that rises in almost everyone's mind is simple. There is no gravity in space to tweet. But that thought is completely wrong. Gravity is not missing in space. Gravity is not turned off in orbit. Gravity is not weak near Earth. In fact, astronauts aboard the space station are only about 400 kilometers above the surface of Earth. That is closer than the distance between many cities on your planet. And at that altitude, Earth's gravity is still more than 90% as strong as it is on the ground. So, why do astronauts float? Why do they feel weightless if gravity is still pulling on them almost as strongly as it pulls on you right now? The answer will shatter the last everyday illusion about gravity. Astronauts are not floating because gravity is gone. Astronauts are floating because they're falling. They are falling constantly, endlessly, forever missing the Earth beneath them. This is the same trick the moon performs. The moon is not held up by mysterious forces. It is falling. But as it falls, the surface of Earth curves away beneath it. The moon keeps missing the planet, The fall never ends. That endless fall becomes orbit. The space station is doing the same thing. It is moving sideways around Earth at nearly 8 kilometers per second. At that incredible horizontal speed, Earth curves away beneath it at the exact same rate that it falls downward. The station is constantly falling toward Earth, but Earth is constantly bending away at the same pace. So the fall never ends. The astronauts inside are in the same free fall as the station itself. They fall together. Their bodies, the walls, the floor, the air. Everything inside the station falls at the same rate. There is no ground pushing up on them. And without the ground pushing back, weight disappears. This is the single most important truth about weight you will ever learn. You do not feel gravity when gravity acts on you. You feel gravity only when something resists your fall. On Earth, the ground resists your fall. In orbit, nothing resists it, so you float. Now imagine standing inside a tall glass elevator. The cables snap. The elevator drops. For a brief moment, only a split second, everything inside becomes weightless. You float. Objects lift off the floor. Your stomach rises into your chest. And then the moment ends, as the elevator crashes. During that brief fall, gravity never disappeared. You simply stopped being resisted. This is exactly what astronauts feel all the time. Orbit is not weightlessness because gravity is absent. Orbit is weightlessness because nothing is pushing back. Once you see this, everything changes. The clouds are not held up by gravity. They fall slowly through air. Birds do not defeat gravity. They fall forward so fast that air pushes them upward. Airplanes do not escape gravity. They fall around the planet along curved paths made of lift. Nothing rests naturally in the universe. Everything that appears to rest is actually being crushed upward by resistance. Now this idea becomes deeply unsettling. When you lie on your bed, the bed is pushing your body upward with equal force to your weight. When you sit on a chair, the chair is pushing into your bones. When you stand on the floor is pushing trillions of atoms upward into your feet. You feel heavy, not because gravity is pulling you, but because the planet beneath you is launching a microscopic counterattack against gravitational motion. This is why standing still is exhausting over time. Your muscles are constantly resisting collapse. In space, astronauts do not need to work against this resistance. Their bodies relax in ways impossible on Earth. Their spines slowly stretch because gravity normally compresses them. Astronauts often grow a few centimeters taller in orbit. Their bones weaken because they no longer need to support weight. Their muscles shrink because they no longer need to fight collapse. Weightlessness is not freedom from gravity. It is freedom from resistance. This is why Earth life evolved the way it did. Bones, muscles, hearts, and blood vessels all formed to survive resistance to gravity, not to survive gravity itself. Your heart pumps blood upward only because gravity pulls it downward, and your body resists the fall. Your legs grow thick only because they resist collapse under the pressure of your weight. Remove resistance, and the entire structure of the body begins to change. This is why astronauts must exercise for hours every day. They run on treadmills strapped to the floor with elastic bands. They lift heavy machines using resistance. Pistons. They simulate weight not to defeat gravity, but to replace the missing resistance their bodies evolved to depend on. Without it, bone density fades, muscles weaken, balance dissolves, vision blurs, even the shape of the heart changes. Weight is not just a feeling, it is a biological necessity. Now the next misunderstanding falls apart. People often imagine that if you could travel far enough from Earth, gravity would slowly fade to zero and you would drift freely. That is not how the universe works. Gravity never becomes zero, it only becomes weaker. Even between galaxies, gravity still exists. It still whispers across millions of light years. Even in the deepest cosmic voids, gravity still shapes motion, however faintly. The reason you float in orbit is not because gravity has faded, it is because you're moving sideways fast enough that you never hit the ground. Now imagine something even stranger. You are inside a sealed spacecraft, floating far in interstellar space, where gravity from any star is extremely weak. The engines ignite, accelerating the ship forward. As speed increases, you feel your feet press into the floor. You feel weight return. You feel heavy again, but there is no planet beneath you. There is no gravity pulling you, and yet you feel weight. From inside that ship, the sensation is identical to standing on Earth. This shows something astonishing. Weight does not require gravity. Weight requires acceleration. Gravity feels exactly like acceleration. This is the deepest meaning of Einstein's equivalence principle. There is no experiment you can perform inside that sealed ship that tells you whether you're standing on a planet or accelerating in deep space. The muscles feel the same, the pressure feels the same, the blood feels the same, the ground feels the same. This means gravity and acceleration are indistinguishable, not emotionally, not metaphorically, physically. And this tells us something frightening about reality. If gravity and acceleration feel identical, then maybe gravity is not an external force acting on you. Maybe it is simply the shape of how motion unfolds in space and time. When the floor pushes against your feet, that push creates acceleration upward. Your body resists that acceleration. That resistance feels exactly like gravity. Remove that acceleration, remove the push, and you enter freefall. And freefall feels like weightlessness. In Einstein's universe, freefall is the most natural state of motion. It is the motion of objects that are following space-time without resistance. Everything in orbit is in freefall. Everything in deep space is in freefall. Even you would be in freefall right now, if the floor did not block your path. The earth is not your anchor, it is your cage. It prevents your natural motion and creates the sensation you call weight. This realization transforms the way you see motion forever. A rock sitting on the ground is not at rest. It is being violently accelerated upward by the surface beneath it. A person standing still is not motionless. They're constantly resisting freefall. A building does not simply sit on Earth. It is pushing against collapse every second of its existence. Everything that feels stable in your daily life is secretly fighting gravity's geometry. Now think about what astronauts feel. They feel like they're floating. They feel like gravity is gone. They feel like motion is effortless. But in truth, they are obeying gravity more purely than you ever have in your entire life. They are following the geometry of space-time without resistance. They are the closest human beings ever come to natural motion. On Earth, you are the exception. In orbit, they are the rule. This flips the entire meaning of gravity on its head. You are not bound to Earth by gravity the way chains bind an anchor. You are held in place by resistance to gravity's natural motion. This also explains something strange about falling. When you step off a ledge, the moment before you hit the ground feels nothing like being pulled. It feels like dropping. It feels like your stomach is rising. It feels like freedom mixed with fear. That sensation is not gravity pulling harder. It is the sudden absence of resistance. You briefly experience what astronauts feel all the time, and your body reacts with fear because it evolved to associate loss of resistance with danger. Gravity itself does not scare you. Loss of resistance does. This truth eventually leads to one of the strangest consequences of gravity. If gravity and acceleration feel identical, then gravity must affect time. Because acceleration affects time. And time under gravity does behave in shocking ways. Clocks near Earth tick slower than clocks in orbit. Clocks near black holes slow almost to a stop. Time itself stretches, twists and warps under gravity. And this is where gravity stops feeling like motion and starts feeling like fate. Because the deeper you fall into gravity, the slower time moves. And at the edge of a black hole, time almost comes to a halt. This is not science fiction. It is real. It is measured. And it is the most terrifying next step in the story. For most of human history, time was believed to be the most stable thing in existence. Space could stretch, objects could move, forces could act, but time was thought to be universal. 1 second for you was 1 second for everyone, everywhere, forever. No matter where you stood in the universe, time was supposed to flow at the same rate. Gravity shattered that belief. Not slowly, not gently, completely. When Einstein revealed that gravity is the curvature of space-time, something extraordinary followed from that idea. If space can bend, then time must bend with it. They are not separate. They are woven together into a single fabric. And when that fabric curves under the weight of mass, time itself starts to behave in ways that feel impossible. Near gravity, time slows, not as a metaphor, not as a visual trick, but as a physical fact. This means the clock on your phone is not ticking at the same pace as a clock in space. The difference is tiny, almost impossible to notice in daily life, but it is real, and it is measured. And without correcting for it, modern technology would collapse. Your GPS does not work because satellites are clever. It works because Einstein was right. GPS satellites orbit high above Earth's surface. They are farther from the planet's gravitational pull than you are right now. Because gravity is slightly weaker up there, time moves slightly faster for those satellites than it does for you on the ground. Their clocks gain about 45 microseconds per day compared to clocks on Earth. At the same time, those satellites are also moving very fast, and motion itself slows time. Because of their speed, they lose about 7 microseconds per day. The result? A net gain of 38 microseconds per day. That sounds like nothing. Less than 1/10 of a millisecond. So small it seems laughable. And yet, if engineers did not correct for this tiny difference using Einstein's equations, GPS would drift by several kilometers every single day. Your navigation would slowly slide off reality. Planes would miss runways, ships would misjudge coastlines, phones would quietly lie to their owners about their true positions. The modern world depends on time bending under gravity. This alone proves that gravitational time dilation is not theory, it is not hypothesis, it is not philosophical speculation, it is built into your daily life. Now imagine moving closer to a much stronger gravitational field, a mountain. At the top of Mount Everest, time moves slightly faster than it does at sea level. People at the top of a mountain age just a tiny bit faster than people on the coast. The difference is far too small for your body to feel, but over a lifetime, it is real. One twin living his life at sea level and another twin living high above it would not age at exactly the same rate. Gravity decides how fast you grow old. Now imagine moving closer to something much more extreme, a neutron star. A neutron star is the collapsed core of a massive star. It is so dense that a single teaspoon of its matter would weigh billions of tons on Earth. Space curves violently near it. Gravity becomes fierce, and time responds accordingly. Near a neutron star, time slows drastically compared to time far away. An observer near the surface of a neutron star would watch the universe outside speed up. Stars would burn faster. Seasons would pass quicker. Entire civilizations might rise and fall, while only years pass for the person deep in that gravity. Now imagine the most extreme gravitational object possible, a black hole. At the edge of a black hole, gravity is so intense that time nearly stops. From the perspective of a distant observer, anything falling toward a black hole appears to slow down. As it approaches the event horizon, its motion becomes sluggish, its light grows redder, its clock ticks slower and slower, and then it seems to freeze forever. From far away, nothing ever truly crosses the event horizon. It simply fades. But from the perspective of the object falling in, everything feels normal. Time flows as usual. It crosses the boundary without noticing anything special. And then deep inside, it is lost to the unknown. Two observers see the same event. They experience two completely different realities. This is not illusion. This is gravity rewriting time itself. Now let this thought settle. If time can slow down under gravity, if clocks tick at different rates depending on where they are, then there is no single, universal now. There is no cosmic present moment shared by the entire universe. What is happening right now for you is not happening right now for someone near a neutron star. Their present is not your present. Their seconds are not your seconds. Time becomes personal, local, relative. The universe does not agree on what now means. This alone is enough to break the human brain. But gravity goes even further. Time dilation is not only caused by gravity, it is also caused by motion. The faster you move through space, the slower you move through time. This was already revealed by special relativity, but gravity adds a second layer to this effect. Near massive objects, you lose time simply by being close. So time is shaped by two things: how fast you move, how deep you are in gravity. This makes time a dynamic landscape, not a universal river. Now think again about astronauts. On the International Space Station, astronauts are moving fast and are also farther from Earth's gravity. These two effects fight each other. Motion slows their time. Weaker gravity speeds their time up. The result is a tiny difference. Over 6 months in orbit, astronauts age microseconds differently than people on Earth. Tiny, but real. Time has split. Now imagine a world where gravity is much stronger. A planet twice as massive as Earth but the same size. On that world, gravity would be stronger. Time would move more slowly on its surface than it does on Earth. A person born there would age more slowly. Their entire civilization would run at a slower clock rate compared to ours. Now imagine a civilization built close to the center of a galaxy, near a supermassive black hole. For them, time could stretch in ways we can barely imagine. Their years might pass while entire ages unfold for distant observers. Gravity quietly becomes a time machine. It separates histories. It separates timelines. It turns the universe into layers of different ticking clocks. And yet, you never feel this in daily life. You feel time flow normally. You feel seconds pass evenly. You feel no bending. Why? Because Earth's gravity is gentle. It bends time only slightly. But that small bending is enough to prove the rule. The rule is this: time is not absolute. Time is shaped by gravity. Now comes the most disturbing consequence. If gravity can slow time, and black holes slow time almost completely, then gravity is not just shaping motion, it is shaping destiny. Imagine falling toward a black hole. From your point of view, the fall takes a finite amount of time. You cross the event horizon and continue inward. But for the rest of the universe, you never quite arrive. Your fall stretches toward eternity. Your final moments become frozen at the edge of time. To the outside universe, your future never arrives. This means gravity can trap events outside the flow of time as we understand it. The future can be delayed indefinitely. This is not just strange, this is terrifying. It means the universe does not share a single timeline. It is fragmented. Now consider the early universe. Just after the Big Bang, the universe was incredibly dense. Gravity was intense everywhere. Time flowed differently everywhere. As the universe expanded and gravity weakened, time gradually relaxed into the steady flow we experience today. This means the early universe aged slower. The first moments of existence were stretched under immense gravity. The baby universe took longer to grow than it appears in simple models. Gravity shaped the rhythm of creation itself. And now, even at the largest scales, gravity still controls time. Galaxies slowly drift. Stars slowly burn. Orbits slowly decay. Black holes slowly evaporate. Each of these changes follows the tempo gravity allows. Now return to your own body. Every heartbeat you feel, every breath you take, every year you age, all of it is measured by clocks that are quietly affected by the mass of the planet beneath your feet. Time is not just passing, it is being sculpted. Gravity is the sculptor. This brings us to a dark implication. If gravity controls time, then if we ever learn to control gravity, we could control time. Not in poetic ways, not in symbolic ways, but physically, we could slow aging, speed processes, change the pace of entire civilizations, at least in theory. But right now, gravity remains beyond our control. We can ride it, we can fall within it, we can orbit inside it, but we cannot shape it at will. We cannot switch it on or off. We cannot shield it, we cannot reverse it. Gravity is democracy at its most brutal. Every mass contributes, no mass escapes, no mass votes against it, and time follows wherever gravity leads. This means something quietly haunting. The strongest gravity anywhere in the universe also owns the slowest time. The deepest gravity wells do not just trap matter and light. They trap moments, they trap futures, they trap history itself. And yet, time does not break completely under gravity. Something even stranger happens next. Light itself begins to curve, not because it feels a pull, but because it has no choice but to follow the bent geometry of space. And when light bends, the universe reveals one of its most beautiful and uncanny illusions. Stars appear where they do not belong. Galaxies turn into rings. The invisible becomes visible. The next chapter of gravity is not about falling, it is about seeing. For thousands of years, humans believed one simple rule about light. It travels in straight lines. You shine a torch and the beam goes straight ahead. You look at a star and you assume the light came straight from that exact point. Straight lines felt safe, predictable, honest, but gravity does not respect straight lines. And when humanity finally discovered that light itself bends under gravity, it was one of the most shocking moments in the history of science. Because light has no mass, it does not weigh anything. It cannot be pulled the way an object can. And yet, near massive objects, light changes its path. Not because gravity drags it like a rope, but because space itself is bent. Light only follows what space allows. This realization didn't come easily. For centuries, even after Newton explained gravity, light was believed to be untouchable by it. Newton himself predicted that gravity might slightly bend light, treating light like tiny speeding particles. But his calculation was incomplete. It underestimated the effect by half. The true explanation would only come after Einstein reshaped gravity completely. In Einstein's universe, light does not curve because it feels a force. It curves because space-time itself is curved. Light always travels straight, but straight now means the straightest possible path through curved geometry. And when space bends, straight paths bend with it. This idea stayed hidden inside equations for years. No one had seen it. No one had measured it. It remained a strange prediction waiting for a moment when the universe would reveal whether it was true. That moment arrived in 1919. A total solar eclipse swept across parts of the world. For a few precious minutes, the moon perfectly covered the sun. The bright sky darkened. Stars became visible near the sun's hidden edge. And for the first time in history, humans had the chance to test whether gravity truly bends light. According to Einstein, the sun's massive gravity should curve the space around it, bending the light of stars passing near its edge. The stars would appear slightly shifted from their true positions. The change would be tiny, less than the width of a human hair, held at arm's length, but measurable. 2 teams of astronomers travelled across the world to photograph that eclipse. They waited nervously for those few minutes of darkness. They captured images. Then they waited months to compare the star positions with their normal locations in the sky. When the results finally came in, the universe had spoken. The stars had moved. Not physically, but visually. Their light had curved as it passed through the sun's gravity. Einstein's prediction was exactly right. In one quiet announcement, Newton's straight space was broken forever. From that day on, gravity was no longer just a pull on matter. It was a sculptor of light itself. Once you accept that light can bend, the universe suddenly becomes filled with visual illusions of breathtaking beauty and deep meaning. Gravity stops being something you only feel. It becomes something you can see. This bending of light by gravity is called gravitational lensing, and it is one of the most powerful tools we have for understanding the universe. Imagine looking at a distant galaxy. Its light begins a long journey across the cosmos toward your eyes. Along the way, it passes near another massive object, maybe another galaxy, maybe a cluster of galaxies, maybe even a cloud of invisible matter. That mass bends the surrounding space. The light cannot travel straight anymore. It curves, it warps, it splits, it focuses. By the time that light finally reaches Earth, the original galaxy may appear smeared, doubled, stretched into arcs, or even wrapped into perfect glowing rings. These are not artistic effects. These are the fingerprints of gravity on light. In some cases, a single distant star can be magnified thousands of times because a massive object passed between it and us. This effect allows us to see stars that would otherwise be completely invisible. Gravity itself becomes a cosmic telescope. This is not poetic language, it is literal. Mass bends light into focus. Now imagine something even more surreal. A distant galaxy sits perfectly behind another massive object from our point of view. The alignment is just right. The gravitational bending becomes perfectly symmetrical. The light wraps into a full circle around the object in front. You see a glowing ring in the sky, a perfect circle of light. This is called an Einstein ring. It is one of the most beautiful visual proofs that space-time itself is curved. The ring is not a physical object. It is not matter. It is pure light bent into a circle by gravity, a cosmic halo created by geometry. Even more unsettling is this. Sometimes gravitational lensing makes entire galaxies appear in multiple places at once. You might see the same galaxy repeated across the sky in different shapes and positions. Each image followed a different curved path through space-time. Each took a slightly different amount of time to reach you. You are seeing the same object at different moments of its past, all at once. Gravity turns the universe into a hall of mirrors. Now here's the part that changes everything. Gravitational lensing does not care whether the mass bending the light is visible or invisible. This is how humanity discovered dark matter. Astronomers noticed that galaxies were bending light far more than their visible mass could account for. Light curved around empty space, where no stars, no gas, no dust could be seen. And yet gravity was unmistakably acting there. Something invisible was shaping space-time. Something massive was bending light. This invisible presence was named dark matter, not because it is dark like black paint, but because it does not shine, reflect, or absorb light. It announces its existence only through gravity, through curved space-time, through bent light. Without gravity bending light, dark matter might have remained hidden forever. We would have no idea that most of the universe's mass does not shine. This alone shows the true power of gravitational lensing. It allows us to see what cannot be seen. Now let's return to the feeling of seeing. When you look at the sun near sunset, the stars near it are not visible because the sky is too bright. But during an eclipse, the bright glare vanishes, and those stars appear close to the sun's edge. And because the sun's gravity bends their light, their positions are shifted. So when you look at a star near a massive object, you are not seeing where the star actually is. You are seeing where gravity allows its light to appear. Gravity lies to your eyes every night. Every star is slightly displaced from its true cosmic position because space-time is curved everywhere. The effect is usually tiny, but it is never zero. The universe you see is a distorted version of reality, gently warped by gravity in every direction. Now imagine the bending near something truly extreme, a black hole. Near a black hole, space-time is curved so violently that light can loop around it multiple times. A photon can orbit a black hole like a planet orbiting a star. Some of that light eventually escapes, reaching distant observers after circling the black hole once, twice, or even more. This creates a strange illusion. You can see multiple images of the same event from different paths through curved space-time. The universe becomes a layered projection of repeated moments. Near a black hole, light does not simply bend, it can be trapped. And if it crosses the event horizon inward, it never comes out again. This means even the fastest messenger in the universe has a limit. Gravity can lock light away. This realization crushes the final illusion that light is untouchable. Nothing escapes gravity's geometry. Not matter, not time, not even light. Now think about what this means for how you see the universe. When you look at distant galaxies, you are often not seeing them directly. You are seeing their light that has been bent, stretched, amplified, split, delayed, and distorted by everything it passed on the way. Your picture of the universe is a map drawn by gravity. Every deep space photo ever taken carries invisible fingerprints of space-time's curvature. Every blurred arc, every stretched smear, every glowing ring is gravity signing its name on the canvas of light. Now something even stranger emerges. Because light is bent and delayed by gravity, it does not always arrive at the same time. In some gravitational lens systems, different images of the same object reach Earth separated by days, weeks, or even years. This means you can watch the same cosmic explosion happen multiple times, the same supernova, the same flicker of a quasar, the same collapse of a star. Each echo arrives on a different schedule, guided by different curved paths. Gravity literally replays the universe. Time itself is split into echoes by the shape of space-time. And this effect allows astronomers to measure distances, masses, and even the expansion of the universe with incredible precision. By studying how long each delayed image takes to arrive, scientists can calculate the invisible structure of space-time between us and the source. Gravity becomes not just a force, not just a geometry, but a cosmic measuring tool. Now pause and let this sink in. You are not looking at a simple universe. You are looking at a distorted reflection shaped by gravity. Your eyes do not see straight. They see curved reality. And that curved reality is quietly telling us where mass hides, where dark matter flows, where galaxies cluster, and where the future paths of light shall go. All of this comes from one simple truth. Light follows space-time. Space-time is shaped by gravity. And once you accept that, the universe becomes stranger and richer than anything humans ever imagined before Einstein. Before we move on, there is one more unsettling implication of bent light. If light bends away from us near extreme gravity, then some regions of the universe may be permanently hidden. Light may never reach us from behind certain gravitational barriers. Some events may be blocked not by distance, but by geometry. The universe does not promise to reveal everything. Now, gravity has already taken away our idea of absolute down. It has taken away absolute time. It has taken away straight lines. And now, it prepares to take away something even more comforting, the idea that falling has an escape, because when gravity reaches its absolute limit, even escape disappears completely. This is where the story turns toward the darkest objects that exist. Objects where gravity wins so completely that not even light can run from it. Objects where space-time collapses into a prison with only one future. Objects called black holes. And that is where the next chapter leads. There is one place in the universe where every illusion about gravity finally dies. No floating, no bending light back outward, no escape routes hidden in clever geometry, no second chances. This is the place where gravity does not merely bend space, it folds space into a trap. A place where time, light, matter and motion all surrender. This place is a black hole. For most of history, black holes sounded like pure fantasy. A star collapsing into nothing. A pit in space that eats light. A doorway to nowhere. Even Einstein did not fully believe his own equations when they hinted that such objects could exist. He thought nature would never allow gravity to win so completely. But the universe had other plans. A black hole does not begin as a monster. It begins as a star. A massive star is born in a cloud of gas. Gravity pulls matter inward. Pressure rises. Temperature climbs. Nuclear fire ignites. And for millions or billions of years, the star exists in balance. Gravity tries to crush it. Nuclear energy pushes outward. The star lives in a delicate standoff between collapse and explosion. But this balance cannot last forever. Eventually, the star runs out of fuel. The outward pressure weakens. Gravity gains the upper hand. The star begins to collapse under its own weight. For medium-sized stars like our Sun, collapse ends gently. The outer layers drift away. The core becomes a white dwarf. Gravity is defeated, barely. For heavier stars, collapse becomes violent. The core crushes so tightly that protons and electrons fuse into neutrons. The star explodes in a supernova. What remains is a neutron star, a city-sized object with the mass of a star. But for the most massive stars of all, even this is not enough. Gravity keeps winning. The collapse continues. The core shrinks beyond neutron pressure, beyond atomic structure, beyond anything we understand. The star's mass compresses into a region so small and so dense that space-time itself breaks. The result is a black hole. It is not an object in the normal sense. It is a region where the curvature of space-time becomes so extreme that no future path leads outward. Every possible direction leads inward. Every possible future points toward the centre. The boundary of this region is called the event horizon. It is not a physical surface. It is not a wall. It is not matter. It is a geometric boundary in space-time. Cross it, and the future no longer includes escape. From far away, a black hole can look harmless. If it is not actively feeding, it emits no light. It makes no sound. It does not glow like a star. It simply sits in darkness, invisible. But everything near it quietly obeys its warped geometry. Stars can orbit black holes peacefully. Gas can swirl around them for millions of years. Whole solar systems could circle a black hole and never realize what they're bound to, but cross the event horizon and the universe changes direction. Inside that boundary, space-time itself tilts so steeply inward that moving outward would require travelling faster than light. And since nothing with mass can do that, escape becomes impossible, not because of force, but because of geometry. This is gravity at its ultimate victory. Not pulling harder, not pulling faster, but erasing the concept of out. Now imagine what it would actually feel like to fall into one. From very far away, the fall begins gently. You drift inward. Nothing dramatic happens at first. Stars still shine. Space still looks normal. Gravity feels no different than orbiting any other massive object. As you get closer, gravity grows stronger. Space curves more sharply. Time for you begins to slow compared to distant observers. They would watch your motion stretch out inch by inch. Your signals would become weaker, redder, slower. From their point of view, you would never truly cross the horizon. You would appear to freeze at the edge, fade, disappear, but from your point of view, nothing special happens. At the horizon itself, you cross it without seeing a line, without feeling a wall, without hearing a sound. The moment passes quietly, and that silence is the most terrifying part, because the real destruction happens later. As you fall deeper, gravity becomes uneven across your body. Your head feels a different strength than your feet. This difference creates tidal forces. You begin to stretch. Your body elongates. Your legs and arms are pulled harder than your chest. Your spine lengthens. Your atoms begin to separate. This process is called spaghettification. It is not poetic. It is literal. You are pulled into a long, thin strand. Molecules tear. Atoms drift apart. Even the structure of matter is defeated. Eventually, you're reduced to a stream of particles falling toward the singularity, the center of the black hole where our equations break. And beyond that, physics ends. We have no theory that can fully describe what happens. At the singularity, space is crushed, time is destroyed, density becomes infinite. The very idea of where and when ceases to exist in any meaningful way. This is not science fiction. This is the limit of science. And yet black holes are everywhere. In the center of our own galaxy sits a supermassive black hole with the mass of more than 4 million suns. It does not consume the galaxy. It does not suck in stars like a vacuum cleaner. It sits in balance with the surrounding stars, warping space-time quietly. Every large galaxy appears to have one. Some black holes weigh billions of times more than the sun. Some were formed in the early universe. Some roam in darkness alone. Some are being born right now as massive stars collapse. These objects are not rare. They are a natural outcome of gravity when it is given enough mass. And they reveal the final lesson about gravity. Gravity is not gentle by nature. It becomes gentle only when mass is spread out. Concentrate mass sharply enough, and gravity becomes lethal. Now something even stranger happens near a black hole. Light can orbit it. There exists a region outside the event horizon where photons can loop endlessly around the black hole in unstable paths. They circle again and again, suspended in curved space-time. A tiny disturbance sends them either outward to escape or inward to oblivion. This means there are places where light does not go straight and does not escape. It hesitates. Gravity can make even light indecisive. Now comes the final humiliation for intuition. Black holes do not just consume matter, they also consume information. At least, that's what it seems. When something falls into a black hole, all details about its structure, its history, its identity appear to be erased. From the outside, only three things remain measurable: the black hole's mass, its rotation, and its electric charge. Everything else vanishes from the visible universe. This creates one of the greatest unsolved mysteries in physics. Does information truly disappear? Or is it somehow preserved in ways we do not yet understand? If information is truly destroyed, then the laws of quantum physics are violated. If it is preserved, then black holes must store it in some hidden way, perhaps on the event horizon itself. This puzzle is still unsolved, even after decades of study, even with our best theories, even with Hawking's work. Yes, Stephen Hawking revealed something shocking about black holes. They are not entirely black, they slowly leak. According to quantum physics, black holes emit a faint radiation, now called Hawking radiation. Over unimaginable spans of time, far longer than the age of the universe, black holes slowly lose mass. Eventually, they evaporate completely. This means gravity's ultimate prison is not eternal, but its lifespan is longer than stars, longer than galaxies, longer than civilizations. A stellar black hole may take more than 10 to the power of 67 years to evaporate. That is not a number your brain can process. That is longer than almost anything that will ever exist. Now think about what gravity has achieved here. It bends time. It traps light. It destroys the structure of matter. It eats stars. It reshapes galaxies. It challenges the fundamental laws of quantum physics. And it does all of this not by acting like a force, but by becoming the stage itself. At this point, the original idea of gravity as a pull downward feels almost childish. Black holes expose gravity for what it truly is, the deepest rule of the universe, written directly into space-time. This is where gravity becomes absolute, not because it is strong, but because there is no geometry left to escape through. But even here, gravity is not done surprising us, because black holes do not just sit quietly in space. They collide, they merge, they spiral together, and when they do, something extraordinary happens. Space-time itself begins to ring. The universe shakes, not with sound, but with gravity itself. These vibrations travel across billions of light years. They pass through stars, through planets, through your body, through the earth. And for the first time in human history, we have learned how to hear them. The next chapter is not about falling, it is about the universe shaking. For most of human history, the universe was something we only saw. Stars shone, planets wandered, galaxies glowed. Everything we knew about space came through light. Even when Einstein showed that gravity bends light and twists time, we still believed that the universe itself was silent. Motion happened, explosions happened, collisions happened, but space itself was thought to be still, unmoving, a quiet stage where the drama of matter played out. That belief was wrong. The universe is not silent, it shakes, and those shakes are made of gravity itself. When Einstein finished writing his equations of general relativity, something strange fell out of the mathematics. The equations did not just allow space-time to curve quietly around mass, they also allowed that curvature to move, to ripple, to travel across the universe like waves on the surface of a cosmic ocean. These were called gravitational waves. At first, even Einstein was unsure if they were real. The math allowed them. But could space-time truly vibrate? Could the fabric of reality itself stretch and squeeze like water? For decades, no one knew. Then slowly, physicists realized something terrifying and beautiful at the same time. If gravitational waves are real, then the universe is not just a place where events happen. The universe itself is part of every event. When massive objects move violently, they do not just send out light, they send out distortions in space-time. Those distortions race across the cosmos at the speed of light, carrying information about what just happened. Not information made of particles, information made of geometry. Imagine two massive stars locked in a deadly spiral. They orbit each other faster and faster, their gravity dragging space-time into a tightening whirlpool. As they move, they stir the fabric of the universe. They create ripples. Those ripples spread outward in all directions, passing through stars, passing through planets, passing through interstellar space like invisible shockwaves. Nothing blocks them. Not gas, not dust, not planets, not walls, not even entire galaxies. They pass through everything. By the time these waves reach Earth, the original collision may already be finished. The stars may be gone. The explosion may be over, but the trembling of space-time continues its long journey. For decades, scientists tried to detect these waves, not with telescopes, not with radio dishes, not with cameras. You cannot see gravitational waves, you can only feel them. And feeling a vibration in space-time itself is unimaginably difficult. By the time a gravitational wave from a distant cosmic catastrophe reaches Earth, it has weakened beyond almost all comprehension. It stretches and squeezes space by less than the width of a single proton. It changes the length of objects by a fraction of a fraction of a fraction of an atom. How do you possibly measure something that small? Humanity answered that challenge with one of the most delicate instruments ever built. LIGO, the Laser Interferometer Gravitational Wave Observatory. Two enormous detectors, thousands of kilometers apart, built in the United States, each one shaped like a giant L, with arms 4 kilometers long. Inside those arms, laser beams bounce back and forth between mirrors, measuring distances with absurd precision. If a gravitational wave passes through Earth, it stretches one arm slightly while squeezing the other. The lasers detect the change. The pattern shifts. The universe whispers. For years after LIGO was built, nothing happened. Silence. No waves, no signals, no tremors in space-time. Some people began to wonder if gravitational waves were only mathematical ghosts after all. Then on September 14th, 2015, the universe finally spoke. Both LIGO detectors sensed the same signal. A tiny rising vibration, a brief chirp, a quick stretch and squeeze, lasting less than a second. But inside that second was the echo of one of the most violent events imaginable. Two black holes had collided, more than 1 billion light-years away. Each black hole weighed around 30 times the mass of the Sun. They spiraled toward each other at nearly the speed of light. The closer they got, the faster they moved. The stronger their gravity twisted space-time, until, in the final moments, they merged into a single black hole. In that final fraction of a second, more energy was released, as gravitational waves than all the stars in the observable universe produce as light at the same time. Let that sink in. More energy than hundreds of billions of galaxies released in a blink. Not as light, not as heat, not as particles, as vibrations in space-time itself. Those ripples travelled across the universe for over 1 billion years. They passed by stars that were not yet born when the merger happened. They passed through galaxies that did not yet exist. They crossed a cosmos that was changing, expanding, evolving, And at the end of that journey, they stretched and squeezed a few kilometers of laser beams on Earth by less than the width of an atom. And we felt it. For the first time in history, humanity did not just see the universe, it heard it. That moment changed everything. Gravitational waves were no longer theory, they were reality. The universe was no longer silent. It had a voice, and that voice was gravity. Now something extraordinary became possible. For all of history, every story we told about the universe came from light. Light from stars, light from galaxies, light from explosions. But light can be blocked, light can be absorbed, light can be distorted. Some regions of the universe never send us their light at all. Gravitational waves are different. They pass through everything. That means they can carry information from places that light cannot escape, including the darkest prisons in existence, black holes. When two black holes collide, there is no light, no flash, no fire, no visible explosion. From an optical telescope, nothing appears to happen at all, but space-time itself screams. The collision sends out a gravitational roar that can be felt across the universe. For the first time, we now have a way to detect black holes, not by what they shine, but by how they shake reality. Since 2015, dozens of gravitational wave events have been detected. Black hole mergers, neutron star collisions, hybrid systems of neutron stars and black holes tearing each other apart. Each detection carries a story written in space-time. When neutron stars collide, something even more dramatic happens. Neutron stars are made of pure crushed matter. When they merge, they not only send out gravitational waves, they also explode with light across the spectrum. In 2017, for the first time, humanity detected the same cosmic event, with both light and gravity. A new kind of astronomy was born, multi-messenger astronomy. The universe could now be seen and heard at the same time. From the gravitational waves, scientists could measure the masses of the objects, their speeds, their spins, their distance, and how space-time itself responded to their dance. From the light, they could analyse the debris, the chemical elements formed, the firestorm of radiation. This confirmed something astonishing. Many of the heavy elements in your body, gold, platinum, iodine, were likely forged in collisions of neutron stars. Not in ordinary stars, not in supernovae, but in extreme gravity-driven mergers that shook the universe. This means every piece of gold you see on Earth may have been born in an event that sent gravitational waves across the cosmos. Your jewellery has a gravitational history. Now imagine this again. Two collapsed stars collide. Space-time vibrates. The vibration crosses billions of light years. It passes through galaxies, through dark matter, through stars, through your planet, through your body, and you never feel it, because the distortion is smaller than anything your senses can detect. Yet it is real. This means your body is being stretched and compressed by distant cosmic disasters all the time. Not enough to harm you, not enough to notice, but enough to be measured. Gravity is not just holding you to Earth, it is connecting you to the most violent events in the universe. Right now, somewhere in the cosmos, two black holes may be merging, and their space-time scream may already be racing toward you. You just don't know it yet. Now think about what this truly means. Gravity is not a static pull. It is dynamic. It moves. It vibrates. It carries energy. It transmits information. Space-time is not rigid. It is elastic. It can stretch. It can squeeze. It can ripple. It can ring like a bell after being struck by massive objects. The universe is not quiet. It is humming with invisible waves. We just learned how to listen. And once we started listening, another terrifying question emerged. If space-time can vibrate, if gravity can carry waves, then space-time itself is a physical thing, not abstract, not mathematical, not imaginary. It has stiffness, it has elasticity, it has structure. Space is not nothing, space is something, and that realization pulls gravity even deeper into the foundation of reality. Now nothing looks the same anymore. Stars are not just balls of fire, they are generators of space-time tremors. Black holes are not just traps, they are drums that beat across the universe when they collide. Neutron stars are not just crushed matter, they are tuning forks for the fabric of existence. And gravity is not just what makes you fall, it is what makes the universe sing. Now we are close to the final truth. Gravity builds planets, gravity sculpts stars, gravity bends light, gravity slows time, gravity shakes space-time, and yet, there is one final role gravity plays that is even larger than all of this. It decides the fate of everything, whether stars are born or not, whether galaxies form or remain dust, whether the universe expands forever or collapses inward, whether time drifts on endlessly or tears itself apart. Gravity is not just a local rule, it is the conductor of the entire cosmic orchestra, and that final role leads us directly to the end of the journey. Because once we understand how gravity shapes the destiny of the universe itself, we understand why this force, so weak in your hand, is the most powerful law that has ever existed. At the beginning of this journey, gravity felt like something small and familiar, a force that makes apples fall, a weight in your legs, a pull you never question. But now, after travelling through curved space-time, bent light, frozen time, black holes, and trembling universes, one final truth stands above all others. Gravity does not just affect things. Gravity decides their destiny. It decides where matter gathers. It decides when stars ignite. It decides how galaxies grow. It decides how the universe itself will end. Everything that exists is locked inside gravity's long, slow decision. Nothing escapes that verdict. At the start of the universe, nothing existed except chaos. There were no stars, no planets, no atoms, no light as we know it. Just a hot, dense ocean of energy spreading outward from the Big Bang. The universe expanded violently, space stretched, energy cooled, particles formed, and for a while, gravity was weak. The young universe was too hot and too fast for gravity to take control. But gravity never disappears. It is patient. As the universe cooled and slowed, gravity began to whisper. Tiny differences in density, places with slightly more matter than others, grew slowly under gravity's influence. These over-dense regions pulled in more matter. That made their gravity stronger, which pulled in even more matter. This feedback loop built the first structure in the universe. Gas collapsed, stars were born, galaxies ignited, clusters formed. The cosmic web took shape. Every galaxy that exists was assembled by gravity pulling chaos into order. Without gravity, the universe would have remained a thin, spreading fog of particles forever. No stars, no light, no chemistry, no planets, no life. Gravity is the reason the universe has shape. Now look at your own world. Earth began as dust, not as a planet, not as a sphere. Just dust grains orbiting a young star. Gravity pulled those grains together. They collided. They merged. They formed rocks. Those rocks formed larger bodies. Those bodies pulled. In more material, heat built up. The interior melted, heavy elements sank inward. Light elements rose upward. An atmosphere formed. Oceans condensed. Every layer of your planet core, mantle, crust, ocean, sky exists because gravity separated matter by weight and pulled it into structure. Without gravity, Earth would not be solid. It would be a drifting cloud. Gravity built the ground beneath your feet. Now consider what gravity stole. Mars once had oceans. Mars once had rivers. Mars once had a thick atmosphere. But Mars was small. Its gravity was weak. Over billions of years, solar wind stripped its atmosphere away. Without strong gravity to hold its air, water boiled into space. The planet froze. The rivers dried. The world died. Earth survived because its gravity was strong enough to hold its sky. Gravity is not just a builder, it is a guardian. It decides which worlds live and which worlds die. Now look at stars. Stars are not peaceful objects. They are powered by gravity and violence. Gravity crushes hydrogen inward. Pressure rises, temperature explodes, nuclear fusion ignites. A star is gravity turned into fire. For billions of years, gravity slowly feeds stars by pulling their own mass inward. When fuel runs low, gravity wins again. It crushes the core. The star dies, sometimes gently, sometimes in catastrophic supernova that outshine entire galaxies. Those explosions scatter heavy elements across space: carbon, oxygen, iron, gold, uranium. Every atom heavier than hydrogen in your body was forged in a star and scattered by gravitational death. Your blood contains supernova ash. Gravity killed stars so you could exist, but gravity is never satisfied with only one victory. It builds galaxies. Galaxies are held together, not by light, not by heat, not by chemical bonds, but by gravity and something even darker. Dark matter. Most of the mass in the universe does not shine. It does not emit light. It does not collide with atoms. But it bends space-time. It shapes galaxies. It creates invisible scaffolding through which gravity pulls stars into rotating spirals. Without dark matter, galaxies would fly apart. They rotate too fast to stay together with visible matter alone. Gravity alone would not be enough. Dark matter strengthens it. Together, they hold cosmic cities in place. Now zoom out farther. Galaxies gather into clusters. Clusters gather into superclusters. Superclusters form vast filaments. Voids stretch between them. This giant cosmic web exists because gravity is working everywhere at once, not as a loud force, but as a quiet organizer, pulling here, weakly tugging there, balancing expansion everywhere else. And now we reach the largest scale of all, the universe itself. For much of the 20th century, scientists believed gravity would one day slow the expansion of the universe, that the pull of all the mass in existence would eventually overpower the initial expansion from the Big Bang, that galaxies would stop flying apart, that the universe would reverse, collapse inward, end in a final crushing fire called the Big Crunch. Gravity was expected to be the executioner of the cosmos, but the universe surprised us again. In the late 1990s, astronomers discovered that the expansion of the universe is not slowing down, it is accelerating. Something is pushing the universe apart faster and faster. This unknown influence was named dark energy. It works against gravity on the largest scales. Where gravity tries to pull matter together, dark energy stretches space itself. Right now, these two titans are locked in a cosmic struggle. Gravity, trying to gather matter into stars, galaxies and clusters. Dark energy, trying to tear space itself apart. And dark energy is winning, at least for now. Galaxies beyond a certain distance are receding from us faster than light, not because they're moving through space that fast, but because space itself is expanding faster than light can cross it. Their future light will never reach us. They're disappearing, not behind walls, but behind the growth of reality itself. In the far future, if dark energy continues to dominate, galaxies will drift so far apart that every civilization will see only its own local stars. The rest of the universe will fade beyond their observable horizon. Gravity will lose its grip on the largest scales. The universe will become cold, dark, empty, and quiet. Stars will burn out. Black holes will evaporate. Matter will decay. Time will continue. Gravity's great structures will unravel. This possible ending is called the heat death of the universe. Not an explosion, not a collapse, just endless fading. But there are other possible endings. If dark energy changes, gravity could one day regain control. Expansion could slow, stop, reverse. Galaxies would rush back together. Temperatures would rise. Space would shrink. Everything would collapse into a final singular state. A big crunch. Another possible ending is even stranger. If dark energy grows stronger with time, it could overwhelm every force in existence, even within atoms. Galaxies would tear apart. Stars would dissolve. Planets would be shredded. Molecules would be ripped into particles. Space-time itself would be torn open. A big rip. Which future awaits us, we do not yet know. But one thing is certain, gravity will be part of the decision. Because gravity is not just shaping objects, it is shaping the future of existence itself. Now return to where we began. Your body, your weight, your fall, your standing. Every breath you take is part of a gravitational system. Every step you take is guided by curved space-time. Every year you age is shaped by gravity's effect on time. Every atom in your body was forged because gravity crushed stars. Every world you see exists because gravity organized chaos. And one day, gravity will decide the final arrangement of the universe you live in. This is why gravity is the most misunderstood force of all. It feels weak, it feels quiet, it feels familiar, but it outlives stars, it outlasts light, it outshapes time, it decides the fate of galaxies, it governs the birth and death of worlds, it bends the rules of reality itself. You do not merely live under gravity, you live inside its long unfolding decision. Every free-falling orbit, every glowing star, every trembling space-time wave, every black hole shadow, every expansion of the universe. All of it is gravity writing the story of existence. Long after your cities fade, long after your species vanishes, long after your planet crumbles, gravity will still be shaping what remains, not as a pull, but as the deep geometry of reality itself. And that is why gravity is not just a force you misunderstand. It is the force that defines what everything can ever become. Gravity began as a simple feeling, a weight in your legs, a fall toward the ground, something so ordinary that it never felt mysterious. But now you know the truth. Gravity is not just what pulls you down, it is what bends time. It is what curves light. It is what builds stars from dust and turns stars into black holes. It is what holds galaxies together and decides how the universe itself will end. Every step you take is guided by curved space-time. Every breath you take is shaped by a force born at the beginning of the universe. Every atom in your body carries the memory of stars crushed by gravity long before Earth ever existed. Even now, as you sit and listen, space-time itself is quietly bending beneath you. And somewhere far beyond what your eyes will ever see, two black holes may be spiraling toward each other right now. Their collision will shake reality. Their echo will race across the universe for billions of years. And one day, long after we are gone, that silent tremor may pass through another world. just as it once passed through ours. That is the scale of the universe you live in. So the next time you feel the ground beneath your feet, remember this: you are not standing still. You are resisting a fall through curved space-time. You are standing on a planet that is racing through an expanding universe. You are part of a story written not in words, not in stone, but in gravity itself. If this journey changed the way you see the universe, share it with someone who still thinks gravity is just about falling. And stay curious, because every force you think you understand is hiding a deeper truth. The universe is far stranger than it looks, and we've only just begun to listen.